So it was a great conference so far, as I said. Let's continue with a few things about four manifolds and mapping class group. The title was chosen a bit by hazard, by random, because it was a conference on four manifolds, and I know a little bit of things about mapping class groups, so I put them together. Let's try to connect them in some way. The main character I want to speak about is not pun intended, is actually the set of homomorphism from phi 1 of a surface group. I see here several notations, sigma g r in the top if I want to be punctured, or r downstairs. Never mind, I think you will mind. And then here G is a group. So I'm taking all homomorphisms from a surface group, which might be punctured into a fixed group. Then I'm taking the quotient by the right action by conjugacy. And also this set is endowed with a nice action on the left by the mapping class group. I can put, just to make shorter, gamma GR. So gamma GR is in the notation of my previous speaker, is mod GR. So this is acting by precomposing on the left by automorphism of phi 1, which respect the conjugacy classes of the punctures, and everything is well defined up to inner automorphism because we have the right action by conjugacy. So this is a main object, and it appears in several places in mathematics, from geometry. Let's say G, the classical object for a compact Lie group, or let's say Lie group, like PSL2R. You're going to find the Teichmüller space as the component of this object. So there are many interesting structures. But today we will take G most often to be a discrete group. And here is how it could appear. Let's say take a four manifold M4, which admit a map into a surface, and two with very few singularities, with finitely many singular points. Well, let's say the typical case would be when on local coordinates f is identified to the map f z1, z2 is z1 square or z2 square. In the case where all singularities arise this way, and if orientation on each chart is compatible with the global orientation, of M4. This is what we usually call a Lefschetz fibration. In dimension 4. But there is another case where dropping the orientation assumption leads us to slightly more general objects called achiral Lefschetz fibrations. A lot of work done to understand Lefschetz fibrations. I must say that to warn that not all Lefschetz fibrations admit complex structures, and the map F is not necessarily holomorphic, but these are typical and very interesting examples of such Lefschetz fibrations. Achiral Lefschetz fibrations are much more general and are still not completely understood. For instance, it's still open whether, put here an open question, whether every simply connected orientable four manifold M4 closed, okay, closed orientable has an achiral Lefschetz fibration over S2, for instance. You see the usual Lefschetz fibrations are connected to symplectic topology. They give rise, for instance, also to almost complex structures. Using Noether formula, it follows easily that S4 does not admit a Lefschetz fibration over S2. There is no Lefschetz fibration. Nevertheless, however, there exist achiral Lefschetz fibrations of S4 over S2. Matsumoto gave a number of constructions which are very interesting in this context of torus fibrations. For instance, you take S3 into S2 Hopf fibration, and then seeing S4 as a suspension of S3, you take just the cone over S3 this way, and you see S4. Then you get the suspension of the Hopf fibration, big H, and being a bit careful about where critical points arise, then you can get here a map with only two critical points. And if you choose them right, then you have, the general fiber is a torus, and there are two immersed singular fibers, which are immersed spheres, and one has a self-intersection which is positive +1, and the other one inside this 4 has negative intersection S4, and that's typically the case which arise in achiral Lefschetz fibrations. So while in some sense they furnish much more examples of four manifolds which can be sliced by this kind of generalized Morse functions. There is an even more general situation where we can take singularities to be those which arise in which has a Milnor fibration. So locally they are determined. They have a disk D4 sent into D2, and here you have in the boundary sphere, you have some link L which is fibered, and the singular fiber is just the cone over some fibered link L inside the boundary, and the map is a kind of suspension. Is a suspension of the boundary fibration, S3 minus neighborhood of L into S1, which corresponds to what happens on the boundary. But actually, it should be something like that. Here is the regular neighborhood of the link, and here is the vertical fibration to. This is also, this is an open book fibration. So you can go to this more general setting. Actually, what we can say is that not all four manifolds admit such singular fibrations. For instance, the sum, connected sum of k bigger than 1 S1 of S3 does not have singular fibrations. So not all four manifolds admit such fibration, exactly the same as such four manifolds do not admit Akira-Lefschetz fibrations. So now what can be said about these singular fibrations? Well, they are more or less, as in the classical case, described by the so-called monodromy. You see, being having only finitely many singularities, you remove them, you remove the critical values, and what, let's say, B inside M4 is the critical locus, and you take F from M4 minus inverse image of B into N2 minus B. This is a regular fibration, locally trivial, and this is, let's say, with fiber. I will always prefer to take fiber to be connected, like in algebraic geometry, with connected fiber. Let's say sigma G of some genus G, and then I'm looking to the monodromy of this locally trivial fibration, and this is providing me with a map from phi 1 and 2 minus B inside the mapping class group gamma G, which is, of course, well defined only up to monodromy. So we provide an element here. And, well, in many cases, one has to take the action of the group on the left to see when two such fibrations, two locally trivial fibrations, are the same as in the realm of locally trivial fibrations. Actually, as in the case of Lefschetz fibration, usual Lefschetz fibration, there is an extra option called relatively minimal. In a Lefschetz fibration, the local fiber here is simply an annulus fiber in a Lefschetz fibration, and the monodromy is just the band twist around the core of this annulus. This is locally around the singularity, but otherwise, here you have the the sigma G generic fiber, and we call relatively minimal left chest vibration if the vanishing cycles are essential curves in the generic fiber sigma G. And there is a similar definition in general. You want that the generic fiber sigma G minus the local minimal fibers to be not to not contain disc or annuli. So in this condition, actually we can say that two singular fibrations, so we can uniquely compactify here. So two singular relatively minimal singular fibrations with fibers of genus at least 2 are equivalent in the appropriate sense if and only if their monodrome is here. Agree. Agree. Namely, they belong to the same orbit of the mapping class group on this set. So, well, there is some form manifold which might be interesting to be studied using this kind of algebraic setting. Now, of course, there are a lot of questions which needs to be understood about the structure of this set. A priori is just a set with an action on it. This is a classical question. I would say that there is first an obvious invariant. Let's say, take first the case when there are no punctures. So we have homomorphism from pi 1 of sigma G of closed surface into a group G. Well, there is an obvious invariant. Let's say I'm taking here sigma G, the fundamental class, into the homology with integral coefficients of sigma G, and I'm taking its image as star. Which is a class, let's call it SC of F, the Schur class, which belongs to H2 of G. Well, it appears that everything acts naturally here. G, the action by conjugacy, doesn't change the image of the Schur class, and an easy argument shows that the mapping class group doesn't change either. So this is an invariant in the sense that the orbits are, this is an invariant of the orbit, and orbit representations, homomorphism with different Schur classes are not, Schur class or invariant are not equivalent. In the other hand, this invariant was well studied by people like Livingstone, Zimmermann, already in the 80s. And they discovered that actually the Schur class does not separate distinct orbits. They are able to separate in a stable range in the following sense. let's say that we have a surface of sigma g plus 1, which is made of sigma g plus adding one more handle here, and then we crush the handle and call that a pinch of one handle. And observe that this is giving map pi 1 sigma g into pi 1 sigma g plus 1 into pi 1 of sigma g plus 1, and call two such homomorphism from sigma g into g to be stable equivalence if up to composing with a number of pinches when we get the map from sigma g plus n. So f and g, or f and f prime, composing with a number of pinches become equivalent with respect to the corresponding mapping class group action on the left. So stable equivalence. The theorem proved by Zimmerman and Livingstone say that stable equivalence of homomorphism into G is completely solved or described by their Schur classes. So the Schur class of homomorphism determines exactly when two such homomorphisms are equivalent up to. This was made even more precise in the case when G is finite. This was made precise by Dunfield and Thurston, who proved that actually there is enough to take for given finite G large enough genus. That's to say, if we have for fixed G a very large genus G, then they become equivalent if G is large enough with respect to the order of big G. Okay. Among all this, there is a particular. Yes?
Sure. The last statement is that if G is finite, then you have a control on H such that they are becoming different.
If G is finite, then there exists some G which is not explicit, such that all homomorphisms from sigma G into the group G are equivalent if and only if their Schur classes agree. Sorry for. Now, there is one particular case which is worthy to be understood when the Schur class is 0. Because, well, it might be of different reason for having that. For instance, H2 of the group G is 0. And the question which appears is a bit more precise, whether all such homomorphisms are elementary, namely they are lifting factor who a free group. those which factor for free group will be called elementary. Of course, elementary, there exists always. You take from pi 1 of sigma g, you take a map into fg, and then, well, if you have enough generators to generate g, then you have lots of such homomorphism. I don't pretend that all elementary are equivalent with respect to the action of the mapping class group, but we are not very far from it. Anyway, we know that they are elementary. We can show that sometimes they are only elementary, and if they are non-elementary, they have some peculiarities. There are some particular examples. So as above, because the Schur class is 0, we know already from the stable equivalence that they become elementary after a few stabilization, after finitely many stabilization. Stabilizations are the opposite of the pinches. So you go to stabilize the surface of genus G to arrive to genus G plus 1n, and then you get them elementary. Is just well, actually the proof of Zimmermann is saying that. Yes. No, I said a free group, but actually I can give you a lemma which will explain that it actually it is exactly Fg, which is 4. But before that, let's call somewhat finitely many stabilization. Well, let's call that number T of F, just to name it. Well, T of F appeared in several places. I think the first time it was exactly defined this way for genus G equals 1, which is not exactly the case I'm considering here, but at least G at least 2, was by Liechti and Julien Marchais in 2017, where they gave a formula for TFF, which actually is working in every genus, as I was saying. Let me put an easy proposition, just saying that there is some topology behind this, is that T of N, T of F, is simply the minimal number of N such that F extends to pi 1 of M free into G, where M free is a free manifold connected, compact connected boundary equals sigma G, and Higard genus of M free is, well, G plus M. So this is just a way to see where the stabilizations are coming from. You have this map from a surface into G. You extend this to a free manifold. Now, the free manifold has some Higard splitting in the general case, or in the generalized Higard splitting. And the number of one handles you need to add to make this work is precisely the number of stabilizations. well, it's not quite effective. If you want a more effective, there is an algebraic formula, but probably it is not enlightening. This algebraic formula is starting from the fact that H2 of the group G is given by the Hopf formula. If G is a free group divided by the normal subgroup generated by some relations R, then H2 of G can be written as FF intersection R by the FR. So if you have a map from pi 1 of sigma G into F divided by R, you take here A1, AG, B1, BG, the usual, one of the usual generator system. Then you take lifts alpha I tilde in F, lifting of F of AI, beta E tilde, lifts of F of BI. Then you take product of A alpha A tilde, beta E tilde from Y1 to G. And you wanted to write, this is an element which is a commutator, is in the commutator subgroup. It's also a relation because it's a pi 1 of surface, and actually it should belong to this subgroup. So it should be written as a product of F J R J, where J go from 1 to N, and what happens with F J belongs to the free group, but R J belongs to R. Well, this is the same N as there. The minimal number, when you choose all possible lifts of AI, F of AI, F of BI, and you write it in this form, the minimal N, it's exactly T of F. This is a way to translate this geometric statement about the Hegar genus of free manifolds standing it. Well, this is more or less classical things coming from René Thom, who interprets the homology as a Bordism. So actually maps from the sigma G to the classifying space of the group G are corresponding to homology classes of such relative Bordism. Okay. Right. It works only in small dimensions, and yeah. So this is the way to say that it's maybe not obvious to compute explicitly the number of stabilization, knowing that the Hegar genus is not easy to compute, even if you know the free manifold. But now you take for the minimal overall free manifolds bounding the surface. So now I will just mention that sometimes, for very different reasons, T of F is always 0. This is a very nice theorem due to, well, I'm putting it as a remark, and maybe I state later if time will be enough. This is due to, is a nice theorem by the late Reznikov in 1997, saying that if G is the fundamental group of a free manifold with positive scalar curvature. So, for instance, G is well, is Z over MZ. Well, Z could be the binary dihedral group, okay, of order 4n. This is the 2,2n group in the Coxeter. Tetrahedral group, icosahedral group. Well, in our terms here is A5, tetrahedral 2, 3. Well, there are many others. Then always T of F is 0. Actually, all homomorphisms into such group G of a surface group are elementary. And the reason is that some deep results on minimal surfaces are saying that free manifolds of positive scalar structure do not have minimal surfaces, but any F can be realized by an immersion of a minimal surface. So there are particular cases, for instance, Z2 free product Z3, most commonly known PSL2Z, is showing that maps from pi1 of sigma G into PSL2 of Z are always elementary. They are always factorizing through a free group. Actually, we can make things more precise also in the case SL2Z, which is corresponding to genus 1 singular fibrations and so on. I don't have really the time to explain why I'm focusing now still on finite groups G. But the reason is that what appears to be interesting is the case when G is a mapping class group, okay? Let's say gamma HS. And we'd like to describe these points. Already in the case of Lefschetz fibrations, these questions seems wide open. Daniel Roux did a lot of progress on finding invariants from this point of view of Lefschetz fibrations. And what would be the first thing to be done by somebody who knows a bit about quantum representation would be to take a representation of the source group of the target group G into some GLV or into a Lie group, to compose and to try to do things by composing the map from here with some specific representation rho up here, and to study the character variety. And in many cases, you have that integrality condition. For instance, if you take the usual quantum representations, that's Gilmer and Gregor Mattbaum theorem about integrality, then you can take a number of finite quotients arising this way. And in some sense, the finite quotients you can get, if you take all of them, they determine everything about the invariance of the type of linear type, let's say, spherical functions, traces, and so on. That means that in some sense, you might restrict to finite groups or to compact Lie groups. But now, recall that we had above the action of the mapping class group, which is acting on by precomposition on the left side. And now I recall you a very beautiful theorem by Bill Goldman in the beginning of this century. Showing that such a path might be led to a dead end if the fact that the action of the mapping class group gamma GR on Hom phi 1 of sigma GR. And here I'm taking G, a compact Lie group. Actually, Bill did prove it for G SU2 at first, and then this was extended by his former students, Privite and Xia, is ergodic. Ergodic means that there are, from the point of view of the measure theory, measurable functions on this space, which are invariant by gamma GR, are simply constant. So actually, this is not leading the geometry point of view in which you take trace functions and other functions defined on the character variety, at least when G is compact, cannot lead to anything useful for our equation, which was to separate points in different orbits. So we have to stick somewhat to finite quotient by imagining that here from gamma GHS we are using, as I said, integrality or whatever. Actually, Zariski density is enough for most of our to take here finite quotients and to look after invariance of the finite orbits obtained this way. Okay, so well, to do that properly, we have to understand what's going on in this particular case. Now the story is not very easy to understand, even in the case when the groups are finite, because what we actually get is some kind of profinite invariance, as you have seen earlier this morning. So let me start first with some discussion about the case when you have simply a free group. So in the case of the free group, you have a conjecture called the conjecture, saying that if you take the homomorphism, now of course to separate points here, one usually take S. It was mentioned before, S means surjective for obvious reasons. Okay, so you take G now, finite, simple non-abelian. Okay, and N is at least free. Now you take Hom S phi 1, well, let's take the free group on N generators into G up to G. And now we have a slightly larger group acting on the left, namely the group of outer automorphism of the free group. And the question, what that? Because this is kind of particular situation we're going to have if we have elementary, well, it's somewhat intermediate. I'm not claiming this is equivalent to the case of classification of elementary, but it's part of the general classification. Well, the Wigold conjecture is simply saying that here, if I'm replacing H by a slightly larger group, but which is in general not much bigger than G, is often just an extension by Z/2. Anyway, here I took all the group of automorphisms. Well, there is only one orbit. What is it saying? It's saying that actually, if you don't look very careful to our problem in dimension 4, actually the invariants you think are meaningless. There is nothing which remains. Well, this if you take G finite, arbitrary, not necessarily simple non-abelian, with mu of G generators, the more general conjecture is that it works for n bigger or equal mu of G plus 1. This is the generalized, still open. There are lots of examples where this has been proved for specific G, and we know that this group has a so that's work of Gilman in the 70s, Evans 83 or something like that, saying that actually we know that out Fn is acting with a large orbit, so as an alternating group. AR on a large orbit of order R, and R is quite big. So we have partial results. This is still unknown in general, but what this is implying immediately, if you look at that, is that we have as a consequence, so the conjecture, if the conjecture will hold conjectures, implies that there are no finite, simple, non-abelian characteristic quotients. Of Fn and at least 3. Okay. Now, this is a bit depressing for those who wanted to arrive to 4 manifolds. So the question was also asked by Lubotsky in the realm of mapping class groups acting on a surface group here. Recall, which is a bit smaller than here, maybe a lot smaller, and he asked whether the same still holds, and actually what we could prove in a joint paper with Pierre Lochak a number of years ago. Is that for any G, at least 2, there exist infinitely many finite characteristic simple non-abelian quotients of phi1 of sigma G. So In particular, we are able to show as a corollary of that there are several orbits. In particular, there are several orbits. For instance, just simply you take those which arise this way as characteristic simple non-abelian quotients, and the projection homomorphism, and you take one which is elementary, because these which are finite characteristic have non-geometric kernel, meaning that the kernel does not contain any class of simple closed graph. Okay, I recall that there exists such that there known that there exists homomorphism in free group into finite groups which have no simple closed curve in the kernel. I think Livingstone again gave example. David Gabay, maybe one of the first examples. Picard constructed one group like that, which was characteristic. The difficulty was here to put all conditions in the same. Simple, non-abelian, and characteristic, and moreover with non-geometric kernel. So in particular, we found that there can be several orbits, all of them distinct. So in some sense, the invariants you could find using finite quotients of mapping class groups might give you some information about distinguishing orbits of the mapping class group on this set. The way to prove just in 2 minutes, well, this is done by means of quantum representations. You take y1 of sigma g, you send it into gamma g1, the mapping class group of a surface with one puncture, and then you take some of the representation into pg, well, I'm putting here some big G, which is a Lie group, real Lie group, linear algebraic Lie group, and here is one of the representations which Renaud described in great details last days. And Thomas Coberda with Ramanujan Santaruban already proved that for generic P, this map should be with infinite image. And actually, what we did prove with Pierre Lochac was to show that the image is actually Zariski dense into a linear algebraic group, depending on the way we want defined over Q or over Q over zeta P, depending on which kind of strong approximation theorem we want, because here, from here, we go to, let's say, I'm putting here by abuse of notation, G of F, bold F Q. Here are points of G into the finite field with Q element, which, well, for suitable Q, such a map exists, and then by the strong approximation theorem due to Nori and another by Weisfeller, one can show that this is surjective, and these are precisely our finite characteristic simple non-abelian quotients, because you know for many of the linear algebraic groups, when you take their values defined over a finite field, they get groups which are not far from being simple. And in most cases, generically, they are non-abelian if G is non-abelian. So I think my time is over now. Thank you again for everything and also for inviting me to give this talk here. Thanks a lot.